So, we were considering post correspondence problem. So, given two sets of words, the instance has a solution if you can find integer I1, I2, Im such that Wi1, Wi2, Wim is equal to xi1, xi2, xim. And given a Turing machine, how can you construct, given m and w, how can you construct an instance of a MPCP, modified PCP? That is what we have seen. Let us take this example. This is a Turing machine which we have already seen, which accepts 0 power n. It accepts 0 power n, 1 power n, right. And given a string like this changes into a x, again goes here, changes this into a y, comes back, changes this into x, changes this into y, comes back, changes this into x, goes and changes this into y, comes back, and when it finds that there are no more zeros, it has to see that there are no more ones, and when it encounters here, it puts a tick mark and halts, saying that the string is accepted. So, it has to accept 0 1, this machine has to accept 0 1. What are the IDs? Q naught, the IDs I will write like this, Q naught 0 1, it changes that into x and goes to Q1, and when it sees a 1 in state Q1, it changes that into y and moves to Q2, Q2 xy, and in Q2 when it sees a x, it moves right in Q naught, and in Q naught when it sees a y, it moves right in state Q3, in Q3 when it sees a blank, it goes to Q4 and puts a tick mark and halt, Q4 xy, and then it puts a tick mark, goes to Q4, and then it has to halt, right. This is the sequence of IDs which leads you to acceptance. Now, from the moves, how do you construct two sets of words for the PCP? Okay. Two sets A and B. The first one is hash and Q naught W, here Q naught 0 1 hash, this is the initial pair. Right. Then group 1 will have every symbol, if you have a 0, you have a 0, you have a 1, you have a 1, you have a x, you have a x, and so on. So, I will rather put it as z, z, where z can belong to 0, 1, x, y, tick mark. Hash, hash I left out, hash symbol. Then group 2 should simulate the moves of the machine. Group 2 pair of words. Okay. What are the pairs? Q naught 0 is Q1 XR. So, Q naught 0 is Q1 X right. When the move is right, there will be only one pair. When the move is left, there will be several pairs. Then Q naught Y is Q3 YR. Q naught Y is YQ3R, there is only one pair because the move is right. If the move is left, you have several pairs. Q10 is Q10R, Q10 is Q10R, the corresponding pair will be like this. Then Q11 is Q2YL, Q11 is Q2YL. where again Z can be any one of this. Then Q1 is Q1Y is Q1YR, Q1Y is Q1YR, the pair will be like this. Then Q20 is Q20L, Q20 is Q20L, Z can be any one of the following symbols, but not hash. Z can be here, Z belongs to 0, 1, X, Y tick mark. For this one hash also I am including. Then Q20 is Q20L, then Q2X is Q0XR, Q2X is Q0XR, and Q2Y is Q2YL, Q2Y is Q2YL. Again Z can be any one of the symbols, so there will be several pairs corresponding to that. Then Q3Y is Q3YR, Q3Y is YQ3, and Q3 blank is Q4, Q3 blank, for that you have hash, is Q4 tick mark, right. So, tick mark Q4. So, these are the pairs corresponding to Z can be, Z belongs to 0, 1, X, Y tick mark, it can be anyone, any other symbol. So, these are the pairs corresponding to the moves. Then which is the final state? Q4 is the final state. Q0 it will change a 0 to a X, and Q1 it will change a 1 to a Y, move left in Q2, and then if it sees a Y it will move right in Q3, and finally when it sees a blank it will stop in Q4. So, the other sets of pairs are is any symbol Z1, Q4 Z1, Q4, Z1 Q4, Q4, Q4 Z1, Q4. The last pair will be Q4 hash, hash, hash. Now, making use of these pairs of words, find out whether this instance, this is an instance of a PCP. This instance of PCP should have a solution if and only if M accepts W. What is W here? M is that machine. What is W? 0, 1, and 0, 1 is accepted, right, 0, 1 is accepted. This is the sequence of IDs for accepting. So, how will you build a two strings from these sets of pairs of words so that they are equal? Okay. So, let us see how we can start. Start with hash and hash. The lower string will be longer, each one will be one ID, and then when you try to match the first string with the second string, the next ID will be created, that is what we have seen. So, hash Q0 0 1 hash, this is the initial pair, right, with this you start, then you have to create Q0 0 1 there. So, Q0 0 when you want to create the first one, the corresponding pair is 1 Q1. So, Q0 0 when you try to create, it will be 1 Q1 here, because you have the pair Q0 0 1 Q1, right. Then any symbol ZZ you can add, right. So, 1 1 hash hash. So, when the first ID is created in the initial ID is created in the first string, what is the next okay, I am sorry, 0 is changed into x. So, this is x, sorry, first move is Q0 0 is Q1 XR. So, Q0 0 is x Q1. So, when you add Q0 0, you are adding x Q1 here, okay, right. So, what is this ID x Q1 1? That ID is appearing there. Now, this ID has to be created here. So, x Q1 1 you have to create. So, what is the pair here? Z can be any one symbol as seen, Z can be 0 1 xy tick mark. So, when you add x Q1 1 here, x Q1 1 here, what will you add? Q2 xy, you will add Q2 xy, then a hash here and a hash here. So, the next ID Q2 xy is created. Now, you must try to create Q2 xy here, right. So, what is the move? Q2 x is x Q0. So, when you write Q2 x, you have x Q0 here, then a y can be written here, a y can be written here, a hash can be written here, a hash can be written here. So, x Q0 y is the next ID and that ID is created. Now, x Q0 y you have to create in the first string. So, you have to choose a corresponding pair Q0 y. Q0 y is y Q3. So, first you add x, you add Q0 y here, corresponding pair is y Q3. So, x y Q3 you got here, x Q0 y, the next ID x y Q3 is created there. So, these two strings have come up to this far, that is the first string has come up to this, the second string has come up to x y Q3 hash. I am continuing from there, right. Now, what is the next move? Q3 hash is tick Q4. So, first you create x, you create a x here, you create a y here, you create a y here. Then when you try to create Q3 hash, you will create a tick mark and a Q4. Q3 hash, in this place you would have got x, y, tick, Q4 hash. Now, you have reached the final ID, you have to start consuming the symbols. So, x, y, tick, Q4, just Q4, hash. Now, again it will start consuming the symbols x, y Q4, just Q4 here, one more symbol is consumed, hash, here x Q4, but only Q4 here, then a hash, what is the last pair? Q4 hash hash. So, you will have Q4 hash hash and only hash. Both the strings have become equal, right. So, you can see that successive IDs are created, and finally, if the string is accepted, the symbols are consumed and you end up with equal strings. So, the PCP has a solution if and only if M accepts W. So, if PCP were decidable, if you can have an algorithm for PCP, then you can use that algorithm to find out whether M accepts W or not, and whether M accepts W becomes decidable, but you know that that is not a decidable problem. Okay. So, PCP is undecidable. Now, we can make use of the PCP to show that ambiguity problem is not decidable. The ambiguity problem is a context free grammar ambiguous? Ambiguity problem is a CFG CFG, a CFG would mean this is the input is a CFG. Now, we can reduce PCP to ambiguity problem. How can you do this? An instance of PCP has two sets W1, W2, WK, two sets of strings X1, X2, XK. Right. Now, you construct a language, this is over an alphabet sigma, all these strings are over an alphabet sigma. Now, consider an alphabet sigma union A1, A2, AK, new symbols. A1, A2, AK are new symbols, they are not in sigma, some new symbols you have added. Now, this alphabet you are considering sigma dash is equal to sigma union A1, A2, AK. Corresponding to this K, you are having case symbols A1, A2, AK. Now, consider a language LA. LA is a set of words of the form WI1, WI2, WIM, AIM, AIM minus 1 up to AI2, AI1, strings of this form, where I1, I2, IM they are all integers between 1 and k. And LB is a language XI1, XI2, XIM, AIM, AIM minus 1, AI2, AI1. Right. Now, this portion is from sigma, this portion is made up of the new symbols. Each string has two portions. The first portion is made up of from symbols from sigma, second portion is made up of the new symbols. Now, you can have a linear grammar for LA, you can have a linear grammar for LB. So, what is LA is actually LA of a grammar GA, language of a grammar GA. What is GA? GA has rules of the form SA goes to W, J, SA AJ, J will vary from 1 to K, SA goes to WJ AJ. Right? It is a linear grammar, and in the linear grammar you have K rules of the form. Wj, if Wj is generated on the left side, Aj is generated on the right side, and you can end up the derivation with that some Wj. So, for each j between 1 and k you have a rule. So, you have 2k rules like this, and using these 2k rules you can generate strings of this form. See, first you generate Wi1 and Ai1, then you generate Wi2, Ai2, in between the non-terminal SA will be there. Then you generate Wi3, Ai3 and so on. Finally, SA will generate Wim, Aim, right. So, this linear grammar will generate LA. Similarly, LB will be generated by another grammar. SB goes to XJ SB AJ, again J will be between 1 and K, and SB goes to SJ AJ. There will be 2K rules for GB, and with these two, it is a linear grammar. With these 2K rules you can generate strings of the form xi1, xi2, xim, aim, aim and so on and so on. First xi1 and ai1 will be generated, then xi2 and ai2 will be generated and so on. Now, consider a grammar G with the rules from GA and GB and 2 more rules and rules of the form star S goes to SA, S goes to SB, where S is the start symbol. Now, you can see that this G is ambiguous if and only if the PCP has a solution. G is ambiguous if and only if PCP instance has a solution. Why? In 2 directions you have to prove. Suppose PCP instance has a solution, then you have to prove that G is ambiguous, and if G is ambiguous, the PCP instance has a solution. Suppose PCP instance has a solution, then you will have Wi1, Wi2, Wim, this will be equal to xi1, xim, isn't it? There will be some sequence of integers such that Wi1, Wi2, Wim is equal to xi1, xi2, xim. Then concatenate with aim minus 1 up to a1. Here also use the same string aim minus 1 up to ai1. This is equal to this and this is the same string. So, they are equal, right, and this has a derivation from SA and this has a derivation from SB, isn't it? This string will have a derivation from SA, this string will have a derivation from SB. So, S derives SA, derives Wi1 etc. S derives SB, derives xi1 etc. So, there are 2 derivations for the same string, and the derivations are all leftmost, it is linear grammar. So, there is no leftmost, rightmost, everything is the same, right. So, you are to have two leftmost derivations for the same string. So, that means G, assuming that PCP instance has a solution, you have proved that G is ambiguous, right.
The problem is any given graph G, any given grammar G is ambiguous.
No, we are constructing a grammar here. See, from the instance of PCP, I am constructing a grammar like that. Given this instance of PCP, I am constructing a grammar like that. And after constructing the grammar, showing that G is ambiguous if and only if this instance of PCP has a solution. So, one way we have proved, that is, if the PCP has a solution, G is ambiguous. The other way around, if G is ambiguous, the PCP has a solution. This is what we have to prove. If G is ambiguous, then you have to show that PCP, this instance of PCP has a solution. Now, the string, any string in the language has one portion made up of sigma, another portion made up of the new symbols, some AIM minus 1 and AI 1, right. And this sequence of symbols determines the order in which these rules are to be applied. They are linear grammars. So, leftmost derivation only one non-terminal will occur in any sentential form, right. And this sequence dictates the order in which the rules have to be applied. If this is the sequence, latter portion of the sequence, that means you should have applied this SA goes to WI1, SA AI1 first, then you should have applied SA goes to WI2, SA AI2 next, and so on. Finally, last rule you would have applied SA goes to WIM AIM. So, this sequence of symbols in the latter portion of the string dictates the order in which you have to apply the rules. So, any string of this form, first portion made up of symbols from sigma and the second portion made up of symbols, new symbols which you have added, that can be derived in only one way in GA. There is only one derivation possible for any such string in GA. Similarly, only derivation is possible in GB. So, if the grammar is ambiguous, that means there should be two derivations possible, at least two derivations. And we know that for any string only one derivation is possible in GA, only one derivation is possible in GB. So, if there are two derivations, that means there should be one derivation in GA, one derivation in GB. So, if you use that the given word G is ambiguous and this WI1, WI2, WIM, AIM, AI1 is generated. Now, if this string is generated ambiguously, there should be one derivation from GA, one derivation from GA. So, there should be another derivation XI1, XI2, XIM, AIM, AI1 in GB. They are the same strings, and this latter portion you remove them. If you remove, it is the same thing. If you remove, you find that WI1, WI2, WIM is equal to XI1, XI2, XIM. That is, you can find sequence of integers I1, I2, IM such that this is equal to that. That is, the instance of PCP has a solution. So, given one instance of PCP, you are able to construct a grammar G such that G is ambiguous if and only if the instance of PCP has a solution. So, suppose the ambiguity problem for G, ambiguity problem for context free grammars is decidable. Okay. Suppose, I will write like that. Suppose ambiguity is decidable. Then what happens? Any instance of PCP, any instance from that instance in this method construct G. Then ask, is G ambiguous? If it is decidable, it should say yes or no. Ask, is G ambiguous? Then you will come out his answer yes or no. If it is yes, PCP has a solution. If it is no, PCP does not have a solution. That means PCP is decidable. You conclude PCP is decidable. But that is not correct. PCP is not decidable. We have already proved that. So, it is a contradiction. And the contradiction is because of the assumption ambiguity is decidable. So, therefore, ambiguity problem is undecidable. Many problems on grammars you can show the undecidable like this. For example, given two context free grammars G1 and G2, is LG1 equal to LG2? Is LG2 contained in LG1? And given two grammars G1 and G2 and regular set R, some regular set R, is LG1 equal to R? Is R contained in LG1? All such things are undecidable problems, and many of them you will prove using PCP. Okay. It is easy. See, actually the first problem to be shown undecidable is the halting problem. Then making use of that, you have shown other problems undecidable. But as far as grammars and strings are concerned, it is better to use some known problem, undecidable problem, which is on strings. Okay, it is easier. So, first you prove PCP is undecidable. Then reducing PCP to that new problem will be easy, because PCP is on strings, right. So, that way the proofs are given. So far about undecidability and decidability, there are many results, many more results, but next we will go on to complexity issues of Turing machines and see what is meant by an NP complete problem, right. So, for that first we see what is a space and time complexity. So, whenever you are writing a program, you are worried about the efficiency of the program, right. What do you mean by efficiency? How much time it will take, right. Usually time is taken as the measure of efficiency, but also another problem which is also of importance is how much memory it will use. Okay. So, both issues, memory, usage of memory is also important in some cases, especially in some problems on computational geometry. Memory also becomes a issue, because sometimes you will be able to get good time measures by paying for that, in the sense that the space will increase a lot. There will be usually a trade off in some algorithms. I am not saying all algorithms. In some algorithms, when you try to improve on the time complexity, number of steps, because you have to use a proper data structure and so on. The data structure should help to search in a quick manner and get some results. And keeping the data structure, you may require large amount of space. So, when you want to improve on the time, you will be paying in terms of space. So, both are important in certain cases, but mainly the time complexity is the one which rules over everything. I mean, that is more important than the space complexity. So, what do you mean by space complexity? We will start with terms of Turing machine. Another thing which we have been studying and insisting is that any Turing machine can be simulated by a random access machine or a register machine, which is more like a computer. Turing machine is not random access, because to get back some information you have to travel back and get the information. But any Turing machine you can simulate with a random access machine, and at most the time in will quadruple, t time is t squared, and you can do that. And similarly the other way around, any random access machine you can simulate with the Turing machine, but time may at the most be t squared. So, polynomial or non-polynomial will not get affected, because whichever model you follow. And this proof is not difficult, but I have not given the proof for the equivalence, it is given in the book. Sometimes later if there is time I will do that, otherwise simulation of register machine with Turing machine and Turing machine with register machine. Okay, it is that proof we can take as a reading assignment and read. So, now we will define time complexity and space complexity in terms of Turing machines, right. So, what do you mean by space complexity? What do you mean by time complexity? Now, the model you consider is slightly different for the two definitions. For the space complexity, you consider an offline Turing machine. What is an offline Turing machine? There is an input tape which is read only, there is a finite control, and there are some tapes which can be used for reading and writing, read write tapes, some tapes, K tapes you can have. Each tape will have a tape head. The input is read only, we can move on this, but within this space, and on this you can read and write on these tapes. The reason for separating the input is because the space, if you do not use a different tape, input you have to anyway read, that means you have to go through all that, space complexity cannot be less than n, right. Whereas here in for accepting this you may use less amount of cells here, for example log n, if this is of length n, you may use just log n cells in any one of the tape and then accept it. It is possible to have space complexity less than n. That is why this definition offline Turing machine is given. Consider the offline Turing machine M. If for every input word of length n, M scans at most Sn cells on any storage tape, then M is said to be an Sn space bounded Turing machine or of space complexity Sn. The language recognized by M is also said to be of space complexity Sn, right. By separating the input, Sn can be less than n also, that is it can be something like log n. If we are not separating the input, you have to read the whole input, so space complexity will be n or more only. That is why this definition. Next. What do you mean by time complexity? In time complexity, you need not have to have a separate thing. Input can be, you can have a multi-tape Turing machine with a finite control and tape heads. You need not separate the input out for defining time complexity, because anyway time complexity cannot be less than n, less than all the cells you have to read one by one and then only accept. Consider a multi-tape Turing machine with k infinite tapes. If for every input word of length n, m makes at most Tn moves before halting, then m is said to be a Tn time bounded Turing machine or time complexity Tn. The language recognized by m is said to be of time complexity Tn, right. Now, it is important whether you are using multi tape or single tape. You cannot just say single tape, because we know that if you have a single tape Turing machine, it can simulate a multi tape Turing machine, right. Any single tape Turing machine can simulate a multi. You have seen how the simulation can be done by having, if you are having k tapes, you can have a single tape with 2k tracks and so on. So, if the time is Tn here, it will be Tn squared here, right, of the order, the general order. So, we just cannot say single tape Turing machine. You have to be careful whether the general definition is given for multi tape Turing machine. If you do it with a single tape, at the most you may be multiplying by another factor, if Tn into Tn factor. For example, you can see that I want to accept WCW, okay. How will you accept WCW? In a single tape, W is here, C is here, W is here. So, you will be marking the first symbol and checking whether it is the same symbol here, come back, mark the second symbol, go and mark the second symbol after C and so on, right. So, you may have to make a number of moves. If this is n 1n, length is n 2n plus 1. For checking one pair of symbols, it has to take n plus n, 2n moves and so on. So, the number of moves will be order n square. Whereas, if you use a 2 tape Turing machine, I have another tape also, and WCW is given here. I want to check whether the first portion before C is the same as the second portion. In the second tape, I start from here and copy this W here. When I see the C, this pointer goes here, but this pointer will be moved here. So, going from here to here and making a copy would have taken n plus 1 moves. Then moving it back to this side would have taken another n moves. Then move them simultaneously and check whether they are the same, another n moves. So, in 3n plus moves, the length is, input length is 2n plus 1. In 3n plus 1 moves, you will be able to check if you have 2 tapes. If you have only one tape, you have to do it in order n squared time. So, whether it is multi tape or single tape is important. General definition is given for multi tape Turing machine, finite number of tapes. So, if for every input word of length n, m makes at most Tn moves before halting, then m is said to be a Tn bound Turing machine or of time complexity Tn. The language recognized by m is said to be of time complexity Tn. Then you talk about, see, in these definitions, conveniently we have said the Turing machine without mentioning whether it is deterministic or non-deterministic. Okay. If you have a deterministic Turing machine, and if it accepts a language with space bound Sn, that sort of class of languages is denoted as D space Sn. D space Sn denotes the class of languages accepted by deterministic Turing machine bounded Sn space bounded Turing machine. Similarly, N space Sn denotes the class of languages accepted by non-deterministic Sn space bounded machines. Similarly, D time Tn denotes the class of languages accepted by deterministic Tn time bounded Turing machines. N time Tn denotes the class of languages accepted by non-deterministic Tn time bounded Turing machines. Now, we know that what is the connection between Sn N space and D space, D time and N time. Of course, that is the main thing. D time, N time, you know that when you want to simulate a deterministic Turing, non-deterministic Turing machine with a deterministic Turing machine, the number of moves may increase exponentially. What about space? Again, I will state some results without giving the proofs. Proofs are in the book, but main results I will just mention. Now, this Tn or Sn, the function that Sn is a function of n, is not it? N is the length of the input, n is the length of the input, and Sn is a function, is the space is denoted as a function of this. When do you say that function is space constructible? What is this definition of space constructible? Sn is space constructible suppose for an there may be several inputs of length n, at least for one of them it should use Sn space. Suppose for all inputs of length n it uses much less than Sn space, then that Sn is not space constructible. You follow? There should be one Turing machine which for any n there should be at least one input of length n for which the machine use Sn cells. Okay? Such a thing is called space constructible, such a function is called space constructible. What do you mean by fully space constructible is for every input of length n it should use Sn cells in a tape. For at least one input of length n if it uses, it is space constructible. For every input of length n if it uses Sn cells, it is called fully space constructible. Now, there is an important result which is known as Savage's theorem. This brings out the connection between if L is in n space Sn, then L is in D space Sn squared provided Sn is fully space constructible and greater than or equal to log n to the base 2. You need not worry too much about this portion, because many of the commonly known functions are space constructible, log n, 2 power n, any polynomial, n factorial, everything is space constructible. So, you need not worry about this portion. Sn is fully, this you need not worry too much. The main point is this: if L is n space Sn, then L is in D space Sn square. Okay. Generally, what is P? P denotes the languages accepted by deterministic Turing machine in polynomial time. the class of languages accepted by deterministic Turing machines in polynomial time. NP is a class of languages accepted by non-deterministic Turing machine in polynomial time. Still it is an open problem whether P is equal to NP is an open problem. Now, what can you say about n space polynomial, let us say. Suppose there is a polynomial Pn, it can be accepted by a deterministic Turing machine in space, right. So, polynomial, this is a polynomial, this is also a polynomial. Okay. So, if it is polynomial, they are equal, n space and d space are equal. So, in the hierarchy anyway P is equal to NP are not known, but definitely P is contained in NP. Whether it is proper inclusion or not, that is the question. Now, this will be contained in n space polynomial, let us say, is not it? This and d space polynomial are equal. Right. Now, d space log n will be contained in P, because in any tape if you use only log n cells, how many number of times you use, it will be still polynomial time, right. So, this will be contained in this, and by a space hierarchy result, this is properly included in this. This is properly included in this, right. But these inclusions, whether they are proper or not, we do not know. But at least one must be proper inclusion, because this one is properly included in this. It looks as though this is proper inclusion, but it has not been proved, right. So, with a brief introduction to this sort of an idea, we shall consider what is meant by a complete problem for a class. For any class, what do you mean by a complete problem, and in general what is an NP complete problem, and Cook's theorem, the next lecture.